Welcome back. We're in chapter 25, 19 I think in your book, on vibrations and waves. And this is some practice we're going to do. Some of this is pretty straightforward. I think you've even looked at it before. So let's look here at the beginning. This is a sine curve. If you were to push the sine button on your calculator and graph it, you are going to get a curve that looks like this. Okay, it's periodic. It's going to go up and down forever. It's going to be it's going to have a certain amplitude. This is the amplitude of that wave. And it's going to have a certain wavelength. This is the wavelength. The wavelength is from the top of the crest to the next, or the bottom of the trough to the next, or any place to its corresponding part on the next wave. So one wave would, say, start here, go up and back, and then down and back, and one wavelength would equal this spot. Okay? So let's look at the question. It's asking with a ruler to measure the wavelength and amplitude. Okay, so I have a ruler built into this gadget here on my iPad, but I don't think you can see it. But I've got it superimposed over top of the waves. You can use a ruler, and I've got rulers that you can borrow. And if you were to put it from somewhere to some corresponding space, you're going to get, in this case, a 7 centimeter wavelength, okay? And its amplitude, remember, is the height above the middle bar, okay, how far away it's going. So if this were a guitar string, and this is where the string normally rests, and you pull it out, that's its amplitude, and then it would spring back and then go the other way and kind of go back and forth, and that oscillation is causing the sound. So how far away you put it will depend on its intensity. So the intensity of sound would be loudness, the intensity of light would be brightness. So it corresponds there. So if I were to measure this, the amplitude would be 1.5 centimeters. Okay? All right, so you have a next definition is of a hertz, and a hertz is a cycle. So if you were to have, say, this oscillation, the string going back and forth, back and forth that way, and it starts here and it goes out to its furthest extent and comes back, and it goes forward again and back again. One wavelength worth, one cycle up and back and up, that's a cycle, in 1 second is a hertz. Okay, so 1 hertz is equal to a cycle per second, and a cycle is just going through one wavelength. How far going through a wavelength in a second. That's a hertz. So here's a question on hertz. A kid on a playground swing makes a complete to and fro swing each 2 seconds. What is its frequency? Well, if its frequency is 1 cycle and it takes 2 seconds to do the cycle, then what is its, how fast is 1 cycle? How many in 1 second? If it takes 2 seconds to do 1 cycle, how much are you getting in 1 second? That's probably the better way to say it. Well, if it takes 2 seconds to go through 1 cycle, how much do you do in 1 second? Well, it would be half a cycle. It would be a half of a hertz. If the period or the time it takes to do is 2 seconds, then the frequency would be 1/2. Now, so the next question obviously is, what's the period? How long does it take? Well, if it happens in 2 seconds, it takes 2 seconds. Look at the relationship between this. 0.5 is equal to 1/2. And 2, how is 2 related to 1/2? Can you see that it's a reciprocal? It's a 2 divided into 1. If it takes 2 seconds, 2 is an inverse. These are called inverses to 1/2. 1 is 1/2, 1 divided by 2. And the inverse is 2 divided by 1. So the period is the inverse, okay, so you can see it this way. Period is capital T, is the inverse of the frequency. The frequency, that's frequency, is in hertz, and the period is in seconds. Okay. So the next question, complete the statements. The period of a 440 hertz sound wave is what second? Okay. Well, the period is inverse of the frequency. And if the frequency is 440, okay, frequency is 440, what is the period? Well, it's going to be the inverse of that, so it's 1 over 440. Okay, I don't know why I put 400. 1 over 440. Right? A marine weather station reports waves along the shore that are 8 seconds apart. What are its frequency in hertz? Well, if 8 seconds is your period, that's the time they are apart, how far it is before they go again. Okay, so that's from crest to crest, so that's one wavelength. If the time between them is 8 seconds, what is its frequency? The frequency is the inverse of it, so it's going to be 1 over 8 hertz, or 1/8 of a hertz. Okay. Number 4, the annoying sound from a mosquito is produced when it beats its wings at the average rate of 600 wing beats per second. What's the frequency? Okay, so a wing beat, let's see, what would a wing beat be? It would be pushing down and then pulling up, getting ready to push down again. That would be one beat. Well, that is a cycle. That's going down and up again and back ready to go forward again. So if that's a cycle and it's per second, then its frequency is going to be 600. And what's the units of frequency? Hertz. 600 hertz. What is the wavelength? Okay. All right, so the wavelength, you're going to have to do a tiny bit of math. Well, we need a formula. So the formula is that the speed, okay, so we'll call that velocity, and we see that the speed here of sound is 340 meters per second. The speed is equal to the frequency, how fast that the frequency is, okay, times the wavelength. So if I know how big a train car is, and I know how many times per second they're passing, I could tell you the speed of the train. That's really all they're saying. So if I've got frequency, we already know that the frequency is 600. We know that the velocity is 340 meters per second. That will make the lambda, or the wavelength, in meters. So what is 340 divided, okay, because you'll have 600 lambda, get lambda by itself, so you're going to divide 600 into 340, and you're going to get 0.57 meters. Okay, the second page. A pitching machine goes haywire and pitches at 10 rounds per second. The speed of the balls is an incredible 300 meters per second. I like to see that machine. So if you know its speed, okay, we saw that speed was going to equal the frequency times the wavelength. We know that the speed is 300. We know that the frequency is 10, and they're asking you for the distance between the balls. So that's the wavelength. That's the meters. So if you take 300 divided by 10, you'll get 30 meters. I hope this is making sense. What happens to the distance between the balls if the rate is increased? Okay, so if this is going up, okay, what happens to this? What happens to this right here? What happens to lambda if frequency goes up? So if 300 stays the same and 10 is increased to 100, what's going to happen to lambda? Well, 300 divided by 100 is now 3. So 30 went down to 3. So if you increase frequency, anything that's on the same side of the equal sign in an equation is inverse to each other, which means if you increase frequency in this case, lambda has to decrease because the other one stays the same. The 300 is constant. So if 10 goes up to 100, then 30 has to go down to 3. Okay, so they're inverse. So this will be the distance decreases as the frequency increases. All right. Next question. Consider the wave generator that produces 10 pulses per second. The speed of the wave is 300 centimeters per second. All right. So we have a speed. Okay, that's 300. We have 10 pulses per second. That's our hertz. That's our frequency. What's the wavelength? Okay, so if speed is 300 and this is 10, what do we got? 300 divided by 10, lambda is going to be 30, and we're in centimeters this time. What happens to the wavelength if the pulses are increased? Okay, so if the frequency increases, what happens to the wavelength? Well, since it's on the same side of the equal sign, as frequency goes up, lambda will go down, so the wavelength will decrease. Okay. Number 7, the bird at the right watches the waves. If the portion of a wave between the two crests passes the pole each second, what is the speed of the wave? Okay. Well, if it takes 1 meter to go 1 second, what's its speed? Well, it would be 1 meter per second. If it takes 1 meter to pass us in a second, what's its period? All right. The period is the time it takes for one wavelength, and this is one wavelength, to cross. Well, what's the time it said? 1 second. So the period in this case is 1 second. Okay. So, number 8. If the distance between crests in the above question was 1.5 meters, and the two crests pass the pole each second, what would the speed be? Okay. Well, if it's longer and it's still going in a second, then it's going to go faster. It'll be that 1.5, just like it said, passing 1.5 meters, and it passes in a second. And what would its period be? Okay. Well, the period is how long it took. It's still going to be 1 second. It was just longer. It was faster going in 1 second. Number 9 is called the Doppler Effect. Okay. When you see a siren, you're going to hear an increase in the frequency of the pitch. It's going to act like it's going higher as, the police car gets to you, and then a lower as it's going away from you. So the question says, when an automobile moves towards a listener, the horn seems relatively what? Okay. So this guy is going to hear the horn that he beat as high. Okay. And what's happening is that these wavelengths are so close that it appears to the listener that the frequency is very close together. Okay, so it's going to sound high, even though the guy hears the horn in the car at a normal pitch, the listener in front of him is going to hear it as high. What's going to happen to this guy? Okay, this guy is going to hear the horn, but those sounds are farther apart in the air, and so he's going to hear the pitch lower than the guy in the car does. Okay, that's called the Doppler effect. So number 10, the changed pitch of the Doppler effect is due to changes in what? Okay, what's different here and here? Do you see that the wavelengths are further apart or closer together? What is that? Is that speed? No, it's frequency. That's how fast they are going together and together. All right, great.